Well, good morning. Firstly, I'm going to give you a health warning on these slides. We had our summer intern working on some of the slides here, and when they work so hard to do some new code builds and so on, you just can't exclude some of the videos, but I wasn't tempted to put last night's build in. Clicker's not working. There we go. So we're all in the cutting edge of technology, and sometimes it gets really confusing to understand words and terminology. And I hope we all in this room do get some downtime from occasionally. We, as the founders of the company, actually have an interesting way of downtime. We sponsor a traditional literary festival in the coastal town in the UK. And it's kind of old school, no e-tablets or anything. It's hard printed literature, which you can go get signed by the author at the end. But literary festivals are a bit specialist, and they have what's called an artistic director, and they're kind of like wedding planners. You do not mess with the artistic director. Sponsors are not allowed to decide who the authors are. But every year, Annie tries to come up with something which is a surprise for us that we can specifically sponsor. Last year, we were struggling with a lot of concepts, and suddenly I find myself introducing a debate between authors. In one sense, the one I have here, which is Alice's book, which is really quite a remarkable book if you get the chance to read it. I think it's published in the US as well, together with a professor at one of the world's only university of AI. And what Alice has been exploring is the whole concept of the word authenticity, and we're not using that word enough, which is why I kind of like it. And though it's got a slightly, we've got the word counterfeit in there, what basically is most lack of authenticity is ignorance or accidental. Only probably 1% of it is actually bad actors. And I think at the end of it, the take-home conclusion there is if we as humans have a big problem understanding authenticity and the provenance of something, are we really going to be able to coach AI to deal that around us? And so I think it's very important when we're looking at AI, there's an awful lot of people taking shortcuts out there, but we need to look at the idea of authenticity on the data we use, particularly training about something as complex in so many different planes that the human is. I think Ori used the terms humans are spatial yesterday, which I think is extremely important. We are. We like our space. And if we do that, I think it's very key that we have the ability, if we start with near ground truth, to be sure of what we're generating there. Preserve spatial fidelity, the complexity, unpredictable of real-world humans. The process of interacting with our behavior is almost infinite. So we have a massive challenge ahead to create avatars that are there. We see a lot of people trying to cut corners with things like synthetic data. Synthetic data worries me because if you train something synthetically on something which is already synthetic, then are you going to get two wrongs making a right, or are you just going to compound the problems? So the nice thing about it is what we're going to show you is a methodology where you can capture very conveniently and quickly the ground truth information of humans that can provide the foundation of decades of research, reminable data. And the process we've got is fully compatible with all the different techniques. I've listed 4 different approaches to developing avatars at the moment. As you can imagine, my favorite tends to be physics, and I'll show you how you can approach this from this kind of data. In terms of what we do, we build these rigs. We're a software company, but we all know there's no such thing as plug-and-play hardware, so we basically certify the hardware, develop our own, which is in there. Basically, what we've done is we run it 60 frames, up to 60 frames a second, so we generate 60 3D frames per second. So here we've had a skateboarder in there with about half a second of his life. We've grabbed one of the frames there, we're processing him. And what we're doing is we're capturing his geometry, in this case, I think, from 28 viewpoints, because there's special zones of interest, together with the corresponding texture, and render that model. It was speeded up a little bit, but that's about a quarter of the time it takes to render that model. So it's very fast. We would expect that model to be accurate in places to 100 microns of linear accuracy. In other places, maybe 500 if it's a flatter surface. So what can we do with this? Well, here's one actually. It's another skateboarder. He hasn't changed his clothes or his colors. It was just done in a different system. This one actually only had 18 viewpoints. So we've got him in there. We saw how quickly he moved through that whole thing. We've captured him. Let's look at his behavior frame by frame. And this is what we mean by ground truth data. If he was interested in coaching, or the skateboard designer was interested in how he interacts with that skateboard, we've pulled out 10 frames or so, and we're looking at each of those frames saying, what is the angle of attack between his trainer and the skateboard itself? And that is as close as you're going to get to ground truth data of humans. That is like having him in the room doing it. Where do we learn all this? Well, we started off in the healthcare environment. Although we had great visions many years ago of avatars and the early metaverse, which we called cyberspace, the people that really wanted us were surgeons that were dealing with pediatric conditions. So we teamed up with the two guys that wrote the textbook, and we developed a capture environment that was resilient to children. Now, just imagine those of you who capture data on a regular basis, attention span. When you go into a clinical surgery, a parent probably has an attention span of 2 minutes, a nurse 40 seconds, a doctor 10, a child 0. So that is a big upbringing. In terms of having to achieve that and so on, it's very key. And it's changed the way people are treated. This is a much older example of where a young child may have a slightly misshapen head. Young Owen there doesn't in this particular case. And in the old days, they used to take a plaster cast and produce an orthotic helmet which would modify the head shape. That's a pretty old procedure, but a hell of a lot more pleasant than that plaster cast. But moving on to a case where we've backported some of the stuff we're doing on machine learning, here's a scenario where we're trying to improve the methodology and costs of treatment and reimbursement. So in this case, we've worked with a team at Wake Forest Hospital. We've back applied some of the work we've been doing on headset modeling to looking at infant skull. So what we're looking at there is, if you do this longitudinally, for example, you can say, is this misshapen head going to grow out naturally, or is this a more serious, which is called plagiocephaly, which can be modified with a helmet? Is it something more serious, like craniocytosis, where the bones don't knit together and you need surgery? And this is a much more way of helping the doctor actually assess what the issue is based on that data. Similar kind of things we've done for years with the US military. We can't show some of the equipment, but we are all seeing out there that most frontline troops now are looking at being wearable or even drone equipped. So therefore, this stuff has to be comfortable. We can't show the night vision goggles that he would be wearing on there, but what we can show that if he tightens his chin strap to accommodate the weight on his head, he can no longer speak into his radio or drink. So a bit of a problem on the front line. Again, this is fully quantifiable. Similar kind of thing is he wearing that backpack well? And so different ways of looking at tightening and loosening straps. It's never that simple. You tighten the straps, it becomes less comfortable and you're less mobile. So that's kind of data in there, applying it to areas like headset and so on. So here is our traditional area where we've looked at human ergonomics and saying, how can we take a replication of somebody and make something out of it, make them more comfortable, improve their health and so on. So why can't we just apply this to AI? And that's what we're looking at here. Because if we take these models, they represent a training set which is a first-generation copy of the person interacting in that environment. First generation. And it's first-generation data you can keep remining. So here we bring the whole lot together with face tracking, body tracking, and hand tracking in a similar model. But let's just break them down. So here's an example of a sample data set of a young lady that's starting to communicate. So as you can see, we can look at each of these frames. They can be automatically marked up, and they can go into a downstream process, which kind of looks like this. So here, the first thing we're doing is we're using, I think, an 84 or 81 landmarks on the head, but we can find different ones and so on. That baselines the first frame, and we can match that frame onto a corresponding image and mesh. What we're now doing is putting that into a mask, which is then going to be deformable by a usable mesh underneath. So we're moving to the deformable mesh on this. Let's just check that it's OK. So we've done a surface comparison here between the derived frame that we're using as a baseline for this and the original frame. So let's bring them all together. And here we have Nathan and his avatar together. Now, it's interesting, and notice how it's cleaned up some of the artifacts on the ears, because you see as the model goes in there, that model's dealt with it. And that's one of the things that we always show in these presentations. We show the raw data, not second generation or manipulated data. But here we have a second generation here. But as you can see, that deformable mesh, because it was based on data probably accurate about 200 microns in a linear side, is a pretty good view of them. When anybody does a show and tell to me of new code, the first thing I say is stop the avatar at some point. Let's compare that avatar to the original donor frame. And while I wouldn't expect to have the same absolute accuracy, I would expect it to preserve the spatiality on it. And that's an important thing we have to look at when we're generating these, because we've still preserved the essence of Nathan's communication here. And, glasses don't, everybody's talking about glasses now. There are a lot of challenges in making these comfortable. I remember I bought the lab a few years, Google Glasses, and nobody could wear them after a while. So there's a lot that we have to understand about how these things are going to interact with the person, how the lenses are going to project correctly back onto the eyes and so on. There's not much space to play with. It has to be right for the person. There was a presentation a couple of years ago from, I think it was Magic Leap, and they showed, when looking at Magic Leap 2, using a 3D MD system, how different the spatial gap was on the ears. We don't all have our ears in the same place on the head. I'd never actually seen it quite like that before in all the years of looking at it. So that's the face. Let's now have a look at the body. So this is quite an old slide, but it shows what can be achieved by inferring what's going on inside the avatar back to using that then to project and understand and quantify the surface. So what we've done with Jess here, we've put a traditional FBX skeleton, and he's not doing anything too dramatic here. We've placed that in, and we've put some arbitrary circumferences around his legs and so on. So we can see how he's moving up and down with those particular areas, how his leg volume, how that cross-section is changing. So this isn't just about a qualitative view of it, it's actually a quantitative view. But if we want to look at things qualitatively, we can do this as well. I love this. This is another classic example. When you scan somebody at this level, you see things you do not expect. So she's extremely fit. I think we did a study on her over a couple of years as she moved from high school to her university environment where she had professional coaching for cheerleader, and we actually saw how her physique changed. But you can see here, as she lands there, look at that ripple going through the thigh. What on earth is it in a physiological sense? Is it muscle? Is it fat? Is it fluid? We don't know, but by looking at these things qualitatively, we can begin to see things which are going to be very important in the future when we understand how to make a wearable for her, or more importantly, how to make a realistic AI-generated avatar of her use going forward. That detail remains there, and it was captured in a few seconds. Now we move on to looking at some older areas. The first one had a simplistic skeleton. When we start looking at superimposing the skeleton back in, it's kind of tricky. And normally, if you took a traditional, what would happen is if she did the crouch there, her spine would go straight up through her head. You've all seen some of these models where it's looked at this area. So we've started to look at how can we make this whole spinal area through machine learning be much more realistic and replicate the kind of movement you would expect there. That one's great, but this one's even worse, sitting down. This is the ergonomics from hell, is understand how to image somebody in detail sitting down and understand what's happened there. So you can see that skeleton that we've put in there is quite resilient to that type of operation. Other things here we showed at the beginning, but here we are. We're actually tracking her face in space. And this isn't an easy one. She's not following any particular pattern. We have no idea where she's going next. But we're interested in her facial expressions as she moves forward. Resolution is a bit low simply because we had to dumb this down to 1080p. But you can see how we're preserving, along with her, the spatial, and isolating the spatial behavior of her face in this case. Here's something much more gentle, but again, I love this slide because there's no dramatic leaping around or skateboards or anything. It's somebody communicating calmly. I think he's speaking a poem. Look at the smoothness of the way his hand's working. That is a kind of avatar we are going to have to generate if we're going to make the metaverse, cyberspace, or whatever we want to call it work. Because we as humans spot irregularities and unnatural movement as quick as anything, and we will get bored if we see stylized avatars which don't have that fluidity of movement that Nathan's got within there. It's very important you start with that kind of data. And finally, the new stuff, and thank you, Eric, the intern, for this. There's some pretty awesome images here. We've been working on hands for many years, not just hands, but also interacting with objects. We decided to take some of the algorithms we were using for the face and the body skeletons and see if we could really start looking at some of the challenges you've got on analyzing hand movement. Now, I think all of the images that were coming up were captured at 60 hertz, but the analysis was done on alternate frames, so it's about a 30 hertz analysis, which is manageable. So here we have an interesting thing, and Eric's studies, what he's looking at is comparative hand movements with the same interaction across a number of different people from different backgrounds. So here we've got somebody in late middle age that's looking at a simple exercise of touching each finger with a thumb. And as you see, there's a lot of occlusion going on within that image. There's a lot of areas in there, but we can isolate the point. We can look at the touch. We get a feeling of the movement of the fingers as they come together as to how that's in place. So if we're looking at interacting with a handset that's way beyond this kind of thing, or a mouse, or we're looking at gesture communication, this begins to start looking at how people behave. So yeah, once you've done one, all hands are the same, right? They're not. So in the top left-hand corner, we've got a young lady, and she can't, no matter how many times we did it, she cannot touch the pinky with a thumb. You can see it kind of goes in that areas. Is it an age thing? I don't know if her dad's still in the audience here, because he did explain to me why she couldn't do it. I don't think he is. But so we've got the situation. But if we look at the others, they're more conventional areas there. So that's just 5 of the people in the study. Clearly, what we're looking at is to quantify that and to say how might that look in composite hand models. We'll go a bit further. These are tricky. So look at the occlusion that's going on when we do the doorknob, when we do those. So we had a couple in here. There he goes. This is tricky stuff. You can't do it with markers. You can't do it with 2D video. You have to understand the occlusions that you're going in and out of. It's not just about the frame that you're marking. It's about what the hell happened just beforehand. Because the way you deal with occlusion, you look at the pre and post frames. And that gives you some idea of what went missing as you went into that gap. So that's kind of state of the art on that one. What we will be doing as this project progresses is look at quantification and being able to compare exactly what the essence of the difference is between, in this case, those 5 people, but I think the sample's a lot larger than that. And no problems with objects. You can see a couple in there where we're actually assembling. Somebody wanted to do something complex, for hand movement, and nothing worse than putting a battery in a Microsoft mouse. They're always the worst ones, I'm afraid. So we had them assemble a Microsoft mouse on top of a transparent table, and you can see what's going on there. It's kind of frozen a little bit, but I think you've got the essence of what was doing there and how we can try potentially to teach a sensitive robot on how they might put that battery in it. I'd buy one. They're always failing. And then there's no problem with spatiality of 2 hands, so a bit of virtual piano playing there. Again, this is something that's going to happen virtually. I don't know quite how in a musical sense you get over the sense of touch without something there, but I can't see any reason why there were things like the North Wrist and a wristband in the FAST that could run disco music. There's no reason why we shouldn't be playing musical instruments virtually if we can get those hands right. But as we all know, every concert pianist has a different structure in their hands. So bringing all this together, this is kind of boring electronic slides. This whole environment we've looked at is not just about producing data that goes onto a cloud. It's also about training devices. So a lot of our customers are putting their devices that they're trying to train in line with this. Wow, did this infrared sensor or time-of-flight sensor actually behave well with real-world data? Oh, it didn't. OK, how do we use the real-world data to coach it to improve on that? And that is a hell of a lot easier than bringing humans in and trying, say, does this work? Because you can keep training on this particular data. So to access that, there's a whole series of routines. This is an example of how this can be a sync system. So that big rig I showed at the beginning, many of our customers have their own devices, some of which we never get to see because they're highly proprietary, or other types of devices where they can synchronize us in line. So I've seen us showing us acting as a master here. We can use satellite-based PTP timestamping, no problem on this. So this can be the timestamp for the whole sequence, because a lot of those little devices don't have timestamping in, to put it mildly. But equally, it can be the other way around. With a mocap system, that could be the master, and we would be the slave within it. And then we could have further, we could act as masters to other slaves going through. It's an open architecture. So to conclude, as we said, it's not just about one person, it's about human interaction. And this is what we're going to be worrying about within not too many years, about how do people really interact with each other, how do they express communication. This is typical of what we often do. This was at the end of an enrollment session, and this couple had, I think, been married about 12 months. And somebody said at the end, hey, you guys, why don't you go on the scanner, and how do you greet each other when you get home in the evenings? So this is extremely genuine, so we see the spatiality of these two people interacting. So again, this equipment has no issue. In fact, that system will go up to 5 people. That's how we generally test the boundaries within it. We walk around the outside a bit like the Wicker Man, I think, and we call that routine. And can we learn something from? Yeah, sure we can. So here we're isolating each face, and we're seeing what is the essence of those interactions of those two as they come together. And you know, if you want to create something that's realistic, you want your avatars to look like real humans in a relationship, you're going to need this type of information to train them going forward. So I'm on to the last slide, exactly on time. I just want to finish with a phrase here. You know, all English people, we use this ghastly term, the devil is in the detail. Fortunately, in German, they use it correctly. God is in the detail, or the detail is in God. So God made us all. We owe him to be able to produce avatars that replicate faithfully that creation. Thank you very much.